distinguished viewers. My name is Zulaiha Ahmed, a PhD student in the Department of Architecture at Istanbul Okan University in Turkey. It is a privilege and honor to present my research titled Beyond the Glass Icon, Reimagining High-Rise Building Envelopes in Tropical Cities. Before I begin, I would like to express my sincere appreciation to Istanbul Okan University and the Department of Architecture for providing an intellectually stimulating environment that encourages critical inquiry, innovation, and interdisciplinary research. As doctoral students, we have the unique opportunity to engage with diverse perspectives, advanced research methodologies, and contemporary debates that shape the future of architecture and the built environment. I am particularly grateful to the academic staff and lecturers within the department whose dedication to teaching and research continues to enrich our scholarly developments. Their guidance has helped me in particular move beyond conventional architectural thinking and has challenged me to engage more deeply with questions of sustainability and sustainable resilience, ecological responsibilities, and energy efficiency. I would also like to acknowledge my professor for this particular course, Sustainable Architecture and Planning, Professor SEMIH ERYILDIZ, whose vast knowledge and commitment to ecological design has been a significant source of inspiration throughout my academic journey. Professor ERYILDIZ's contribution to ecological planning, sustainable urban development, and environmental design has helped shape contemporary discussions on the relationship between architecture and ecology. Together with Professor Demet ERYILDIZ, he co-authored the important work ETURE, Ecological Design and Planning, a publication that advances ecological thinking within design and planning discourse. This book highlights the necessity of integrating environmental systems, ecological intelligence, and principles of sustainable development into architectural and urban decision-making. Their work reminds us that architecture should not merely occupy space, but should actively contribute to the health and resilience of natural and human systems. Their ideas provide an important foundation for the research I present today. Over the last century, the glass-clad skyscraper has become one of the most recognizable symbols of modern architecture. From North America to Asia to Europe to the Middle East, increasingly in Africa, and most especially in Nigeria. Highly glazed towers have come to represent economic progress or prowess, technological advancements, and global urban identity. Yet, while these buildings may perform effectively or be aesthetically pleasing, especially in climates that are more of temperate climates, their widespread replication, especially for us in tropical cities, raises important environmental and architectural questions. Tropical regions are characterized by intense solar radiation, high temperatures, elevated humidity, and heightened climate vulnerability. In such conditions, excessive or extensive use of glass facades often contribute to excessive heat gain, increased cooling loads, higher energy consumption, and reduced environmental performance of buildings. Consequently, more contemporary high-rise buildings in tropical cities have become heavily dependent on mechanical systems to maintain occupant comfort. Now, what I am doing today, or what I'm presenting today, therefore, asks a critical question. Can we move beyond the glass icon and develop buildings or building envelopes that are more responsive to our climates, that are more ecologically intertwined, and they look critically into the human well-being, drawing on ecological design principles, biomimetic thinking, material innovation, importantly, climate-responsive strategies, and regenerative design approaches. This presentation explores alternative pathways to reimagine high-rise building envelopes in tropical cities. The objective is not to merely criticize the glass facade, no, but to investigate how architecture can become more adaptive, more efficient, more resilient, and ecologically integrated within our environmental context. It is my hope that this presentation contributes to the ongoing discourse on sustainable development and offers practical insights for the future of high-rise architecture in tropical regions. Thank you, and I look forward to sharing my findings with you. All right, so from the foregoing, my topic is beyond the glass icon. And today, we are challenging the pervasive glass icon in tropical architecture. What I am doing is I will explore how reimagining high-rise building envelopes can lead to sustainable urbanism. This presentation today introduces different approaches to design. What I aim to do is move beyond purely aesthetic considerations and focus on performance, especially for the tropical climates. Let me begin by examining the current urban challenges. Tropical cities face immense pressure from rapid urbanization. These drives demand for high-rise structures. The glass curtain wall has become a global symbol of modernity, from the works of Mies van der Rohe to the works of Le Corbusier. The aim of this presentation is to identify climate-responsive envelope strategies that enhance environmental performance and energy efficiency in tropical cities. Now, through a thorough literature review, I have been able to identify bioclimatic design principles and climate characteristics that help to promote building envelopes or the design of building envelopes in tropical cities. Now, while designing, especially for building envelope designs, there are variables and parameters that must be considered. From the optical angle, which looks into absorption or reflectance, and emissivity, to thermal comfort, which talks about or looks at insulation and the thermal mass, which is the main building envelope, to the physical components, which we're talking about openings, window to door ratio, window to wall ratio, external shadings, and then to the geometry. We're going to be considering, or we must consider, orientation and the shape of the building. Now, in this paper, I also looked at case studies. I analyzed case studies from Kuala Lumpur to Riyadh and Cairo, how these case studies were able to look at their tropical environments and mitigate issues of solar heat radiation in their high-rise buildings. So what we're going to be doing now is we'll be looking at the evolution of the glass facade, the historical context of the evolution of the glass facade. Now, the mid-20th century saw the rise of the glass facade, which was particularly popularized by modernism. Architects like Mies van der Rohe championed transparency and minimalism. This international style was often prominent in almost all cities, but it disregarded local climate conditions. Glass facade became a global symbol of progress, and it showed prowess. However, this aesthetic bias created a conflict, especially for tropical zones. The high window-to-wall ratios showed an increase in solar heat gain and glare. Now, this result is significant, especially when it regards energy consumption and cooling loads. And what happens is this penalty affects the energy demand of buildings because it needs to create thermal comfort for occupants. Now, glass-heavy buildings are popular across climates, but often perform poorly, especially in hot and humid environments. From the foregoing, my topic, Beyond the Glass Icon, Reimagining High-Rise Building Envelopes in Tropical Cities. This presentation will be challenging the pervasive glass icon in tropical architecture. What I'll be doing today is explore how reimagining high-rise building envelopes can lead to sustainable urbanism. My presentation will introduce different approaches to design. What I aim to do is move beyond purely aesthetic considerations and focus on performance in challenging tropical climates. Now, let's begin by examining the current urban challenges. Now, let's look at the vital role of the building envelopes. The building envelope in itself is merely a physical interface between the interior and exterior environments. It is very critical that we understand that the building envelope is more than just a scheme. It is a critical interface that regulates heat, air, light, and moisture flow. Its functions include thermoregulation and solar control. Now, it must balance daylight admission with weather protection. An optimized building envelope significantly boosts energy efficiency, no doubt. Now, if we understand this, then we know the key to bioclimatic design principles. Thermoregulation, daylight admission, solar control, and water protection. Very, very important. Therefore, what are the core principles of bioclimatic designs? Bioclimatic designs fundamentally transforms how buildings interact, how they interact with each other, and how they interact with their environments. We view architecture as a filter. What happens is it carefully matches climatic factors to human comforts and needs. Now, this is very important. This matter is very important because it moves us beyond merely enclosing space, which we all think the building envelope functions as, to actively shaping the indoor climates or climatic conditions. Now, optimal orientation is very important. Natural ventilation is very important. Effective shadings are all important. They are not just features. They are basically core principles of bioclimatic designs. These elements work in connection with one another to reduce reliance on mechanical systems, making buildings inherently more sustainable. Now, how can we see, or how can we translate these buildings into advanced design strategies? Now, building on these core principles of bioclimatic designs, we understand that there are advanced envelope design strategies that must be considered in order for us to build with beautiful facades in tropical cities. We know that advanced envelope strategies offer sophisticated solutions for climate control, from double skin facades. For instance, it creates a ventilated buffer which significantly reduces heat transfer and improves acoustic performance. To smart glazing. Smart glazing technologies are dynamic. They naturally or dynamically adjust to slow intensity, which optimizes daylight while minimizing heat gain. And then we also have the adaptive facade system. These adaptive facade systems, they represent the pinnacle of envelope design strategies. What this does is it responds in real time to environmental changes. These innovations allows us to precisely balance daylight admission with thermal performance. Now, what we'll see next is how these strategies apply across different climatic zones. Now, our comparative climate analysis reveals distinctive challenges and tailored strategies across various regions. Kuala Lumpur, which is located in Malaysia, is a tropical rainforest and demands deep overhangs to combat high humidity and heat. Now, in contrast to Riyadh and Cairo, which are hot deserts, it requires reflective glass and external screens to mitigate extreme solar radiation. Abuja is a tropical savanna, and it benefits from a holistic climate smart envelope approach. Now, understanding these regions or regional nuances is crucial for effective bioclimatic design. Let's see what happens in Malaysia. If we look at this building, the Menara Mesiniaga in Malaysia, it exemplifies bioclimatic principles through its innovative design. The circular floor plates minimizes the surface area exposed to solar heat gain, a critical factor in tropical cities or tropical climates. The crucially spiraling sky courts integrates vertical gardens and provides both shade and communal spaces. Now, this design demonstrates how form can directly serve function, and in turn reduces energy demand while enhancing the occupant's experience. Now let's move to another building, which is the Diamond Building. Now let's move to the Diamond Building in Putrajaya. This building showcases another advanced approach to energy efficient design. Its distinctive tilting facade is a self-shading mechanism which effectively reduces direct solar radiation. Now, furthermore, it has a central atrium. This central atrium maximizes natural daylighting and allows for deep penetration into different floor plates. Now, this integrated design strategy significantly lowers cooling loads and increases, of course, daylight or natural lighting, reducing artificial lighting requirements. As we can see, what this case study is doing is it's highlighting the diverse ways bioclimatic principles can be applied. Now moving to our third case study, which is the Al Faisalia Tower in Riyadh. This building provides a compelling example of climate-responsive design in an extreme desert environment. As you can see, it has a unique pyramidal form, and the facade technologies directly addresses the intense solar radiation in Saudi Arabia. What we see here is a high-performance reflective glazing working in concert with external shading fins to minimize heat gain. Now, furthermore, what I'm seeing here is the design incorporates thermal buffer zones, which strategically reduces cooling loads on occupied spaces. This integrated approach demonstrates how architectural form and material science can mitigate harsh climate conditions, which is building on our bioclimatic design principles. Moving on from Riyadh, where we will be looking at the smart village in Cairo. This smart village showcases passive cooling strategies which were adapted for hot climates. What is happening here is the traditional shading elements were reinterpreted as modern mashrabiyya. These elements effectively block direct solar radiation. Perforated facades naturally offer adjustable shadings and daylight control, which demonstrates flexibility in environmental response. Now, the office layout, as you can see, are optimized for natural ventilation and natural daylight penetration, which emphasizes spatial efficiency. This approach highlights how traditional wisdom can inform contemporary sustainable designs, much like the Al Faisalia Tower's innovative solutions. Now, moving on to the technical analysis, sky courts and ventilations. Sky courts are formation of different elements or different solutions that help to enhance building performance. Now, what this slide is doing is we're looking at the role of these different sky courts in natural ventilation, which is a critical component of bioclimatic designs. Sky courts, as vertical formations, they create pathways for cross ventilation and they leverage the stack effect to extract hot air. Now, what we're looking at, we have the sky roof, the sky garden, the sky courts, and the sky entrances. These different elements or different solutions help in ensuring a comprehensive solution for cross ventilation and to leverage on the stack effects in order for it to extract hot air from high-rise buildings. Now, what this does is it enhances a building's ability to self-ventilate, reducing reliance on mechanical heat ventilation and cooling. Ultimately, these passive airflow strategies improve thermal comfort and occupant health, which builds on our bioclimatic principles, which we observed in our last case study in Cairo. Moving on to local contexts, our focus now will shift to Abuja, examining the current architectural trends and their climatic implications. Now, this is an example of a building in Abuja, the Central Bank of Nigeria, which exemplifies institutional heritage. The Central Bank of Nigeria in Abuja utilizes deep-set punched windows for passive shading and thermal mass. In contrast, newer corporate buildings in Abuja's CBDs increasingly featured glass curtain walls without external shading. These modern shifts has led to significant solar heat gains, and a lot of buildings are having excessive energy demands, which is increasing the cooling loads and increasing higher energy costs. Now, this underscores generally the urgent trend to climate responsive designs, which echoes technical analysis, which we just discussed previously. Another key example is the NRS headquarters, which employs a modern double glazed aluminium facade system. It is critical to its thermal performance, especially because of Abuja's hot climate. The glazing accounts for 30 to 40% of cooling energy demand, making it a primary driver of building energy consumption. Now, what double glazing does is it reduces cooling loads by 15 to 25% compared to single panel alternatives, delivering significant energy saving. Strategic design elements, however, complements the facade systems for integrated thermal management. Operational practices and potential enhancements, so low emissivity coatings, external shadings can further optimize energy performance. Seeing how current trends in Abuja often overlook climate responsive designs, let's synthesize these findings into a more clear understanding. This approach integrates specific design strategies with their real-world implementation and core benefits. Geometric optimization as seen in Menara Messiniaga, which reduces surface area to volume ratios, significantly lowering heat gain and integrating daylighting. The diamond building atrium, which minimizes the need for artificial lighting. High-performance facades such as Al-Fasalia building, which reflective glass manage extreme solar radiation effectively, and passive ventilation, which was exemplified by our smart village. These smart village, as we saw, enhanced comfort without mechanical cooling. Now, these examples or these case studies, if we look at them, they directly translate into improved building performance. Conclusion: building on our synthesis, we can now draw a clear conclusion about moving towards climate smart cities. The benefits are substantial, especially for tropical cities, from reduced cooling energy use to enhanced occupant comforts and sustainable urban development. This represents a critical paradigm shift for architecture in tropical regions. We must balance innovative designs with environmental sustainability, and we must prioritize functionality over pure aesthetics. It is not just about efficiency, it is about creating more resilient and livable urban environments. So what does this mean for the future? Looking ahead, several key areas will shape the evolution of climate smart envelopes. Digital integration is very paramount. We need real-time sensors for dynamic control, no doubt. We also need AI-driven management systems for optimization. And we also need smart materials that adapt automatically to solar intensity. We have to update our building codes to mandate bioclimatic design principles. We have to provide incentives for developers who adopt climate responsive or climate smart technologies. Then we establish our localized energy performance benchmarks for tropical cities. In the long term, we can have or conduct monitoring of existing climate responsive buildings. We can develop localized simulation models for specific tropical microclimates. And finally, we can investigate the cost-benefits ratio of advanced adaptive systems. Now, holistically, we can see that with the integration of these various climate-responsive strategies, from bioclimatic to ecological, we can see how it has improved the building performance and the energy use in certain buildings, especially from Riyadh to Cairo to Kuala Lumpur and to Nigeria as well. It will be very, very critical in the future for designers and architects to ensure that they integrate bioclimatic design principles in their designs, especially for high-rise buildings. Thank you very much for listening, and do have a wonderful day.